Imagine you wake. You reach for your phone. It is dead, no lights flicker. No hum of machinery. Outside the sky is still blue. The sun rises. But the sun is gone, a void, a silence. The sun has been replaced. What if we swapped our sun with another object in the universe? Not a star like ours, not a supernova. Something entirely different. A black hole, a neutron star, a gas giant, a rogue planet, a white dwarf. Each one borrowed, each one exchanged, as if the sun were a toy in a cosmic game. What unfolds then is not fantasy. It is science, it is math, it is possibility. We begin. The sun is a yellow dwarf, 4,600 million years old, a perfect furnace, a glowing orb that gives life. Its mass defines our orbits. Its light rules our days. Its heat makes water liquid. Its gravity keeps us bound. Remove that sun, replace it. Everything changes. First object, a black hole. Imagine the sun replaced by a Schwarzschild black hole of the same mass. Invisible. No light. Only gravity. We feel the pull. The Earth orbits as before, but the sky is forever dark. No dawn, no dusk, no warmth. Only radiation, background, and stars. Alternate. A neutron star. Squashed matter. Intense gravity. A sun's mass crammed into a sphere the size of a city. The gravity near that object is brutal. Surface gravity millions of times greater than Earth's. Intense radiation. Pulsar beams alternate, a white dwarf, smaller, hotter at first. Slowly cooling. Dense but with far less mass than our sun. Its light faint. Its heat low. Alternate, a red supergiant, enormous, colossal radius. The edge of the sun brushes over Earth orbit. Swallowing planets alternate, a gas giant like Jupiter, only if we scale up mass. Or a rogue planet drifting in emptiness. Each replacement comes with capabilities. Each with consequences. Let's examine first the black hole. Mass equal to our sun. Radius about 3 kilometers. No fusion, no light. No solar wind. Just gravity. It bends space-time. It curves light around it, the perfect darkness at center. Tidal forces near the event horizon unimaginable. But at Earth's distance, gravitational pull same as our sun if mass is identical. Orbits unchanged. But no warmth. No photosynthesis. No light, a neutron star. A core remnant of a massive star. 1 teaspoon weighs billions of tons. It births gamma rays, sometimes pulses. Magnetic fields trillions of times Earth's. Radiation lethal even from light years away. If placed at the sun's position, the Earth would orbit it. But life would be blasted by high-energy particles. The sky alive with pulsar flickers, a white dwarf. Dead star, dense ember. No fusion, slowly cooling. Emits light by stored heat. Initially hot, possibly tens of thousands of Kelvin. Still luminous. But output low compared to a burning star. Warmth dwindles with time. A red supergiant. Magnitude lumbering star. Massive, swollen. Its envelope extending far. Maybe, if large enough, would engulf Earth's orbit. Even if not, its outer layers are tenuous gas. Its core unstable. After a short lifespan, collapse or explosion. Light glorious but deadly. Compare with our real sun. Our sun supplies electromagnetic radiation, visible light, ultraviolet, infrared. Solar wind carries charged particles. Its fusion converts hydrogen into helium. It balances gravity with pressure. It gives Earth its seasons. It sets the climate. Historically, it has been remarkably stable over billions of years. Life evolved under its consistency. In astronomical context, objects like black holes and neutron stars are born in cataclysms, supernovae. White dwarfs are the remaining husks of sun-like stars. Red supergiants are hothouse giants near end of life. We know their luminosities, lifespans, radiation, and behaviors from observation. Now imagine the scene. Earth, our moon, the solar system. We wake to news the sun is gone. Instant swap. No preamble. At midnight across continents, the swap occurs. Light from sun ceases, or is replaced by light from new object depending on what it is. Step 1. Immediate aftermath. Light dies. Day becomes night. Temperatures begin to drop. Air begins to cool. Photosynthesis halts. Plants have minutes to hours before energy reserves used up. Step 2. Heat loss. Without solar radiation, Earth radiates heat into space. At first, surface cools. Atmosphere loses warmth. Water vapor condenses. Clouds freeze. In days, freezing reaches mid-latitudes. Step 3. Ecological collapse. Plants die. Herbivores starve. Then predators. Food chains collapse. Oxygen production slows. CO2 builds, but without plants to consume it. Oxygen drops. Step 4. Atmospheric changes. Without sunlight, chemical processes shut down. Ozone layer no longer sustained. UV background still arrives from distant stars and cosmic rays. But damaged atmosphere. Step 5. Effects on weather. Winds cease. No solar heating of atmosphere. No convection. Weather patterns collapse. Storms dwindle. Precipitation stops. Hydrological cycle frozen. Step 6. Ice. Water on surface freezes. Oceans form ice sheets from top down. Lakes freeze solid. Sea ice grows. Under ice, oceans stay liquid for longer, insulated by ice. Life may persist in deep oceans. Step 7. Geological cooling. Earth's core still hot. Geothermal energy remains, but surface cold. Tectonic activity continues. Volcanoes may release heat and gases. Some microbial life around vents survive. Step 8. Human survival. Infrastructure fails. Batteries, generators run out. Food supplies spoil. Society struggles. In darkness, panic. Attempts to maintain heat by burning fossil fuels. But supply limited. Coal, oil, natural gas yield heat and smoke. Air quality worsens. People cluster near heat sources. Step 9. Long term. After months, perhaps a year, average surface temperature falls to 50 degrees or lower. The atmosphere begins to liquefy under cold. Nitrogen, oxygen liquefy. Oceans fully ice over. Only deep subsurface or hydrothermal vents remain habitable. Now different replacements lead to variations. If the replacement is a black hole of solar mass, darkness stays. But gravity same. Orbit intact. No radiation. Life extinguished quickly. Only residual heat inside Earth can sustain microbes for some time. If a neutron star, initial radiation lethal, Earth would likely be sterilized by gamma rays. If far enough shielded, maybe life underground could survive. If white dwarf, there is light, but luminosity far lower, comparable to a dim star. Warmth insufficient. Plants struggle. Ecology fails. Eventually, Earth gets cold. Life retreats to geothermal pockets. If red supergiant, initially enormous brightness, variable output. Light floods planet, possibly searing. It might engulf Earth's orbit. If not, intense heat and radiation bake the surface. Life scorched. Then collapse. Then supernova. Cataclysm. If a gas giant or rogue planet replacing Sun, mass too small to sustain gravitational orbits as ours. Earth would not maintain orbit. Gravitational effects disastrous. Planets thrown into chaos. We compare to historical extinction events. There has never been an event where a star vanished, but Earth has survived asteroid impacts, supervolcanoes, ice ages. Life has proven resilient, yet nothing in Earth's record matches the sudden loss of solar energy. Scientists estimate that without sunlight, surface temperature drops below freezing within a week. Within a year, the average temperature would plunge to 240 degrees Celsius. Only deep-sea vents and subterranean life remain. Terraforming research reminds us how dependent we are on solar input. Climate models show collapse of photosynthesis in days, animal extinction in months, human extinction in years without alternative energy. All this is logical. All this is inevitable if the sun were replaced. But suppose replacement object is tuned. Suppose it emits some light. Suppose artificial luminosity. Perhaps humans build massive mirrors or fusion reactors to compensate. Perhaps space habitats powered by geothermal or nuclear energy survive. Pockets of life. Enclaves and bunkers in deep earth and caves. Perhaps microbes under ice persist in oceans for thousands of years. Perhaps when Earth's core cools, those too die, but life lasting longer. Conclusion grows darker. The bigger picture emerges. Humanity, fragile. Civilization, reliant on a single cosmic furnace. Ecosystems built around solar cycles. Our orbit, gravity, climate, photosynthesis, seasons woven by the sun. What does this tell us of our place? That we orbit in a narrow window of possibility. That stars are not interchangeable. That light is not a convenience but a necessity. The what if forces us to ask, how resilient are we? Could we survive if our star failed? Could we engineer substitutes? Could we escape Earth? Could we carry life elsewhere? What if the sun is replaced, but not by a monstrous object, but by a different type of star? A red dwarf? A blue giant? What differences would follow? Could Earth orbit stably? What would the skies look like? What would life become